last evening or in this afternoon, already like that, we are the survivors for this intensive week. But then I'm pleased to introduce you Arcelino Lobato from IMPA, and he is going to talk completing Thurston combinatorial presentation of branched covers. Please.
Obrigado. Tá funcionando, né? So, obrigado. Firstly, I would like to thank the organizer and the scientific committee for this great conference and for the opportunity. So today I'm going to discuss about the problem of to present combinatorially a ramified cover, a branched covering of the two-sphere. This is related to a question posed by Thurston. So around 2010, in a working group, he came up with that questions. What are the shapes of rational functions? So in particular, he was interested to determine a simple model for a rational map encoding its branch information, and for which we could reconstruct that object and distinguish it. Then, okay. So, for what reasons? Reason to ask or to be interested on this matter of questions. So, a very general reason is to simplify, try to simplify complex structure from another simple ones that encode the essential information of the object of the theory. Another one that is very common in complex dynamics is to construct some objects with a desired properties. So as we saw yesterday in the talk of Caroline, so construct combinatorial models for moduli space, for instance, moduli space of some complex dynamics system. Discover new invariants or get some tools to understand deeper ones that you have already, and classify and code and that are some reasons. Some prominent realization of this kind of consideration of point of a text a problem. So the first one I will not say much about, but I can, if you are interested, you can go to me and ask afterwards. So it's the Grothendieck theory of the sons d'enfants that describes all the Riemann surfaces that are defined as complex curve over the algebraic field. And I put this because this is a real theory, and all the Galois theory and theory of algebraic numbers are conjecturally following from this theory. And because there we see some phenomena that Thurston realized several times, that in that point you have some topology and combinatorial, and from these two data, the geometry and arithmetic become determined, and vice versa. So in Thurston have that kind of thought that topology determines geometry, and dynamics contain both now. And so in dynamics, some great realizations is the construction of the post-critical finite maps that are a class very, very, very important in the area. So I put here two ways where you associate a combinatorial object, and from it you construct and understand very well your main object. For Dylan Thurston has given a new characterization, a new version of the biggest theory in the area, using graphs. Perry, Cannon, also using graphs, and Tanley also. Bishop, again, has constructed the first example of transcendental mapping, post-critical singular, with wonder domains. Rational functions don't has wandering domains. So this was the first example for that class of the dynamical system. And for last, Ermin and Gabrielov using a bit graphs and provided a proof to a conjecture known as Shapiro's conjecture. That is a problem on enumerative geometry, but in the simplest case, this reduces to count rational functions up to post-composition with automorphism. So two rational functions are identified up to a change of coordinates on the codomain. And the conjecture says that if a rational function has all of its critical points real, then up to post-conjugacy with Möbius transformations, the map is a map with real coefficients. Okay. And using the theorem that I show you, I gave a proof very constructive and totally combinatorial, except for the use of human mapping theorem. Okay. So anyway, the main object is a branched covering. So what is a branched covering? Is a surjective map for us. The codomain will be always the sphere. So for a genus D surface to a sphere, all the surface here will be considered with a prefixed orientation. And so that locally, the map is like the picture. So it is a map that sends a z to some power, okay? That power is the local degree of the point for that map. If that number is greater than 1, so it's a critical value. Around, the function is not injective. The image of a critical value is critical point is a critical value. And the degree is the cardinality of a fiber of a non-critical value, of a regular point, okay? So here's some examples. Every rational function, polynomial or a rational function on the sphere, a human sphere, is a branched cover. This is the local structure of a holomorphic map. Also from any non-constant meromorphic function. oops. Here, another example, no analytic. We have torus, and you consider the quotient by the involution. Involution, in this case, imagine that the origin is the unity square. So you quotient out by the involution. Z goes to minus z. Then you have this fundamental domain. This part, the top are defined by the involution. At the end, we will get a sphere. So this defines a degree 2 map from the torus to the sphere, okay? And as I said, the main problem is to describe combinatorially branched cover. So the object, the combinatorial object that I will associate to a branched cover comes from this picture. So the core idea is to consider your map, then you will your branched cover, so you take a Jordan curve passing through the critical values, then you push this by the branched cover. So I imagine like this will appear. So, and if you color the two components on the sphere separated by that Jordan curve, and you can push out back that coloring to the surface upstairs, and then you get this nice drawings, and that will be the object that I will describe completely. And from which that will encode all the information essential information associated to a branched cover, okay? So, nomenclatura, some vocabulary. A cell graph is one skeleton of a cellular decomposition of a surface, okay? You have two examples. Alternating phase coloring for a cell graph is what you see on that picture. You can define this formally, but this is to associate a symbol to the face in such a way that adjacent face has to be different symbol associated to it, okay? And I will give a name to the Jordan curve that capture the critical values. So I will call it a post-critical curve. Actually, a post-critical curve is the isotopic class relative to the critical value, but today we can think it as simple the curve, okay? Simply the curve. And we will also be considering it with a coloring of the two components, okay? So then that picture that you obtain when you take the pre-image of the sphere with the Jordan curve containing the critical value and with the coloration of the two components, I will call it a pullback graph. So give it a branched cover, you take a Jordan curve passing through its critical value, and you color the two faces of the two components, and then you pull back it, you get what we call a pullback graph of the surface relative to that Jordan curve, okay? So here we have two examples. That one is very interesting because this was firstly drawn by Klein, and the picture is very, very, is super surprising how it could draw and also calculate the expression of the function giving this. Here we have a pullback graph of the torus covering the sphere. Okay. Then, how structure we can start from highlight from a pullback graph. So the first one is that drawing that you obtain on the surface is a cell graph. So the complement of the preimage of the Jordan curve are topological disks, okay? Okay, that is enough. And as we saw in the picture, we can color this object. So any pullback graph admits a coloring of its face. It's the pullback of the coloring upstairs on the surface on the sphere. The number of face colored, base color are the same. So if the degree of your surface is D, then you have D faces of each colors, okay? This cause for instance, in the yellow part, every point has D preimages. And by the continuity, that point has to be on different faces here, okay? Because if you have 2 points, 1 point here with 2 preimages on the same face, upstairs, it will be, if you connect it by an arc inside the face, it will be projected on a trivial loop. But the map restricted from that face to its image is a homeomorphism, is a local homeomorphism. Then the lifting of that homotopy must be trivial upstairs, but not, because you are assuming that you have 2 points. So, and given a pullback graph, every subsurface bounded by cycles that left when you travel around it. The preferred color, the A color, here is the yellow one, are left to your left side, okay? Then in that component, there are more A face than the B face, so more yellow face than white face, as you can see here, okay? So I comment that picture is the picture, a picture associated to some example that Caroline showed yesterday on his talk for the period 3 anyway. And here is the pullback graph of the second iterate of this guy. When your post-critical curve is invariant, then if the preimage of that curve by any iterate will give you a pullback graph also. Because by the invariance, the critical values will be on that base curve, okay? Then another important property is that one that says that if when two faces of the same colors has three or more vertex in common, then that vertices must appear in the same order around that two faces, okay? Oops, sorry. So here, when the color here is the preferred one, so when you travel around it in the positive sense, you pass from the point A, B, C, and around that face in the same order. But if you do this in that example, we'll go from A, B, C, but if you travel around that other face, we'll A, C, then goes back and you get to the B, okay? So this cannot occur. Okay. In the planar case, this is not appears. You don't have homology, so that is the difference. I have to take care about the time, so I will say also now that is the condition additional to the partial answer given by Thurston. So Thurston asked the question and provided a solution to the most simple case for branched covering of the sphere and with the most simple possible configurations of critical points. Each point, critical point having a degree 2 and with distinct images, so like a Morse map. Okay, so as I said, Thurston considered that class of generic branched covering. All critical points are simple, that has degree 2, and the images are distinct. And for that class, he provided an answer to his question that is the following. Give any four regular graph drawn on the sphere. He was only considering branched cover from the sphere to the sphere, okay? And with that simple property. And so for any four regular graph drawn on the sphere, that graph is realized as a pullback graph by some branched cover if you believe that graph is a cell graph. So its complements are made by topological disks. The number, you can color it alternately using two colors, the faces, and we end up with the same number of face color by color. And the local balancing condition is that for any Jordan curve made by edges of that graph, that left the A faces on the left side, is traveling according to the orientation, then that component must have more A face, strictly more A face than B faces, okay? Então, so any graph with that proposition, you can construct a branched covering, realizing that graph as a pullback graph and vice versa. Okay. So the main goal is to present a full general version of that theorem. Okay. So for any criticality and genus, so you have okay, and the critical point doesn't anymore most to have degree only 2, and you can have now more than one critical point with the same image. So. But note that the balance conditions is strictly related to the topology of the sphere, no? Because you choose a Jordan curve passing through the critical values, and then you color it and pull back. And but on a surface of high genus, not always a simple curve and separate the surface into 2 parts. So you are not allowed to talk about to count to distinguish. Okay. So the problem is how to generalize the local balance condition to high genus. Okay. For that, I introduced this notion that cobordant multicycle. What is that? So if you have a cell graph that admits A-B alternating phase coloring, then a cobordant multicycle is a collection, as you can see here, is a collection of cycles made by edges of the graph, okay? In such a way that collection of cycles form the boundary of a subsurface. And we also ask that when such cycles are positive, that when you travel in the positive sense, the preferred color, the pink faces, are left to your left side. Okay. Here, I delete the other faces. So that is the subsurface. And the number of faces of pink faces is greater than the blue faces. We have only one blue face in this. Okay. So the global balance conditions, the definition is the same. The same number of is colored by color, and the local balance is that for any cobordant multicurve, the number of A faces inside it is strictly greater than the number of B faces. Okay, so that is the local balance condition in high genus. Okay, here we have some examples. The time is running out. Oh. Here we have a planar example that is globally and locally balanced. Any curve cycle that you choose here, boundary and peak faces will, in the interior, you will have more pink faces inside it. That is an interesting example that is locally balanced, but not globally. You have more pink faces than blue faces. That one is locally balanced. That cycle here in this region you have 2 pink faces and 2 blue faces. So it's not locally balanced, but is globally balanced. And that is another example on the torus, that is locally and globally balanced. Okay. Proposition, the definition of local balance given here is equivalent in the planar case to that one that Thurston introduced. So using only one Jordan curve, okay? It's a simple exercise. Then coherence. As I said, not the global and the local balance conditions are sufficient for the realization problem. So in the plane, all the local balance is equivalent. It implies actually the coherence that condition. Okay, so it's not necessary in the planar case. So cell graph is coherent if always that two faces have three or more points in common, that vertex should appear in the same order around. Okay. And that is a cohomological condition. Here you are dealing with cohomology in the elementary way, so funny. So I don't have time to go into the proof, but the elements are appearing here. For instance, remember that when I have a pullback graph, if I will label the critical values, they appears around its face in the same order. Okay. So if it's 1, 2, 3, in infinity is the black correspond to the black point here is a preimage of the infinity. So around the yellow faces, that numbers appears increasingly. Okay, and that this labeling is globally consistent. That is the meaning of the cohomological word that I use. So easily you can enumerate around its face, increasing the number in the positive sense that you walk, but depending on the graph, this could not be possible to do this for every face simultaneously, okay? Where it was. So for instance, here, that graph is globally balanced, locally balanced, but not coherent. That this face is, and that dashed here doesn't realize has that condition. Okay, so if you start to try to enumerate the mark the vertex. So for instance, you start with 1 here, so 1, you goes back and up here 2, then you go and you will be here 3, okay? But if you continue on this, that other face, that meet that we started here, so 3, 4, 5, 6, 7, 8. So labeling traveling around one face, here we will have to label 2, and from the other face 8. So that is the non-consistency that appears when you don't have the coherence condition. Okay. Well, so a balanced graph of any genus is a cell graph that is globally, local, and coherent. Okay. And then the theorem, the general version is that any cell graph of any genus is a pullback graph. That is, there is a branched cover and a postcritical curve, so that graph is the preimage of the postcritical curve by that branched cover, if and only if the graph is a balanced graph. Okay. So I have some 5 minutes. So one remark, but well, this is a generalization of the partial answer given by Thurston. So it implies it. Okay. It says more. It says that the conditions that Thurston introduced are sufficient in the planar case. And here, I not put here, but the theorem also cover all self-covering of the sphere with different, not generic, no, any one. So now you can have some critical value with a point with degree greater than 2, and if I draw better, all fibers with more than one critical point above, okay, on the fiber of the critical values. So any possible branched cover from this sphere to this sphere are covered in particular by the theorem, okay? So, obrigado. I have 3 minutes, so I have some. I don't mention anything about the dynamics, but this is a very. There are some applications. And for instance, the understanding of the branched cover using this allowed me to answer a question made by Luna and Sean on to characterize all polynomials that has a fundamental domain with technical conditions for to perform matings with Kleinian groups. And also, if you, in the case of a branched covering of the sphere, if your pullback graph, your postcritical curve is forward invariant, okay, then let's denote like this. So this graph will be a pullback graph for the infinity rate. Okay, and for instance, if I guess not put here no image, no, but let's see here. This is for the second iterate. If the supremum of the diameter of the cells decreasing uniformly, okay, and the critical orbit of the critical points of this map are finite, then that graph, that condition on the decreasing of the faces determine the topological class of that branched cover. So any combinatorial class, in the sense of Thurston, is a topological class for maps for called expanding, for what you have that condition on the decay, uniform decay of the size of the cells. Okay. So yeah, thanks for this.